Goedemorgen allemaal. Good morning, everybody. We're still waiting or expecting some participants, so we'll wait a few more minutes before we start. Oké, we hebben nog niet iedereen binnen. Maar ik denk dat we toch maar moeten starten, gezien de tijd. Voor de Nederlandse deelnemers, aangezien we een aantal sprekers hebben die Engelstalig zijn en een aantal deelnemers waarvan Nederlands niet de eerste taal is, is er iemand die problemen heeft met het feit als we naar Engels switchen? Ik hoor en zie niks in de chat, dan ga ik vanuit dat we naar het Engels overgaan. Good morning everybody. Welcome to this webinar about resource recovery from sludge. My name is Matthijs Pleiner. I'm project manager for the TKI program and I'll be moderating this webinar for today. If we can go to the next slide, please. You've all had the program, of course, but just a quick recap. We'll start in a minute with a welcome word from Bastiaan Lammers, Manager of Operations at NWP. After that, I'll be giving a short overview of the opportunities that the TKI program provides companies to help the development of new innovations. Then we have presentations from Leon Corving, Julian Munoz-Sierra and Sjoerd Kerstens about their innovations in resource recovery from sludge. And then Maarten Schaasma and Daria Krajic will be presenting about the opportunities in the Netherlands and the Balkan region. And after that, we'll have a discussion in which you're more than welcome to participate. And if everything goes according to plan, we'll still plan to finish around 11:45. Then if we can go to the next slide, I would also like to give the word to Bastiaan.
Yeah, thank you, Matthijs, for the introduction. My name is Bastiaan Lammers. I started working for NWP actually last year in June, and I'm glad to welcome and open this session today that we organize, of course, together with the Water Alliance and Envaqua. This is TKI is an important program for us, and I just wanted to take the opportunity maybe to clarify a little bit on the NWP organization and how this program is placed within the organization as well. Can we go to the next slide, Matthijs? Yeah, so since June, we had quite a change. Since January, we had quite a change in the NWP organization. And since January, we are organized in 5 geographical regions that you can see on top. And each of these regions, they have a regional manager. but also the members that are very central are underneath. You can see the NWP members. And in this new organization chart, we really strive to make the connection between market intelligence, which we collect in the regions, and business intelligence, which we collect on the bottom with the business relationship management team. We do that through the programs, the teams, and the platforms that we have. And the TKI platform is very important in this, just like other programs as well. And water and agriculture, and the recollection of nutrients that we discussed today is very important in this link, in which we try to make opportunities as well in the regions and connect them to the proposition of the Dutch water sector. So I welcome the discussion very much. I look forward to see some of the presentations, and glad to see the high turnout as well. I see 19 participants at the moment, so it's good to see everybody online. Thank you for your time. Back to you, Matthijs.
Thank you, Bastiaan. As I said in the program, I'll be telling you now something about the opportunities that the TKI program offers. If we can go to the next slide, please. There's in the last year or last couple of years, the government formulated 25 missions within 4 societal challenges, and in order to stimulate cross-sectoral collaboration. The main 4 societal challenges are energy and sustainability, agriculture, water and foods, healthcare and healthcare and safety. If you think about, for example, energy and sustainability is also including circular economy, the climate agreement. If you look at the food and agricultural sector, it's also about water quality, food quality, and in healthcare, it's more about resistance against antibiotics and life sciences and health. And you see at the bottom, there's a sort of overarching key technologies, and that's where more than just 2 sectors come in. And you can think about, for example, developments in the biotechnology industry. Nonetheless, every top sector, so to say, has its own focus area. So if we can go to the next slide. Here you'll see the 4 main topics within the water technology top sector. The first one is to take care of clean and safe drinking water. You can think about technologies about removing and measuring microorganisms in water streams, or harmful substances, or how to better use natural treatment of water and soil, or a balance between water demand and availability to create more self-sufficiency. The second topic is the reuse of water as the recovery of resources, basically what this webinar is about. And you can think about importance or the creation of processes, products that find a demand in the market and that can compete with the production of raw materials through normal ways, so to say. But also water itself as a primary raw material, and of course the smart application of water. The third one is the generation and saving of energy through water or with water. You can think about innovations about using surface water and groundwater as a source of sustainable energy, or the development of aquathermal applications. And the last one, the smart measuring for the water infrastructure or the water end infrastructure. Those are applications in the ICT industry, artificial intelligence, maybe even virtual reality, to make a better and more sustainable use of the infrastructure that is at hand, well, especially in the Netherlands, and to make, to measure quality of water. So basically anything that is related to ICT and water. The government has several ways to fund or support support innovation. So if we can go to the next slide. Here you see that there's one major program that is called, that is aiming at public-private partnerships. And companies can submit a proposal together with knowledge institutes, and the knowledge institute then submits to the TKI Water Technology office, which will then submit it to the government. And for every €1 of private investment in every research project, the government will add 30 cents of funding that is then used to support more research and innovation. That is one of the larger, so to say, schemes or larger projects. But there's also smaller vouchers or other ways to support it. So if we can go to the next slide. Within the MET regeling, MET is standing for SME innovation stimulating in the region and through the top sectors. And the top sectors is what I explained at my first slide. And basically this funding scheme is based on regions. Every region has defined its own most prominent sectors, and they can differ per region. For example, if you're based in the southern Netherlands, then water is not one of the primary industries, so to say. So you can go and ask for a voucher or submit a proposal at state level. There's three vouchers or three subsidy schemes. The first one is the knowledge voucher. This goes up to 3,750,000 euros. And this is, if you have, as a company, you can submit a question to a research institute, and thank you. You can submit your question to a research institute, and they can do the research on your behalf, or will do the research for you. Then the second one is the feasibility studies. This goes up to 20,000 case, 20,000 euros per funding. That's the maximum, or 40% of the eligibility costs. This one is very popular. At the beginning of this year, on the day that the submission opened, there was the total amounts requested was 9 million euros, whereas the available budget was only 3 million. So that gives you an idea about the high demand for this voucher. Then the last one is the R&D cooperation projects that can be submitted with several SMEs. There's two tracks within this scheme. The smaller track that goes for projects up to 2,000 euros and a minimum of 50,000 euros, and the larger track that goes between 200,000 euros and 350,000 euros. So this is a quick overview of the schemes that are available. Apart from those subsidy schemes, there's also what we call the innovation makelaars, or innovation brokers in English. And you can request a meeting with one of the innovation brokers if you have a question about if you need help with finding, for example, a partner for your innovation project, or if you have a question about how to go further with the development of your innovation. NWP and Water Alliance both have innovation brokers available. So if you have any question, then you can reach out to either organization. And in both cases, I would be the first person to contact. If we then go to the next slide, please. I mentioned already that there's a lot of cooperation in the subsidy schemes with Knowledge Institute. And here there's an overview of the Knowledge Institute that you can collaborate with in the TKI or MET subsidy scheme. So for example, WETSUS, TU Delft, KWR, those are a few of the knowledge institutes. Then that's very quick an overview of the TKI program. This was also my last slide. Well, the next slide is that if there's any questions, you can raise them now through the chat, or you can email me at the email address in the slide, and I'll be happy to answer your questions by email or by phone. That's it for now. I don't see anything coming up in the chat. So then I would like to introduce the first speaker that's going to talk about innovative examples. Our first speaker is Leon Korving. He has a background in chemical engineering and has more than 15 years experience in bringing innovations to the market, and especially innovations about the sustainable use of water, energy, and resources. He has his own company, FRO, and in that company he aims at the sustainable use of energy and water. And he has several other positions, among which the scientific project manager in WETSUS, where he's focusing on the research team about the recovering of phosphate from wastewater. Leon, the floor is yours.
Thank you, Matthijs, for the introduction. Can I have the next slide? Yes, so I will be presenting the vivianiet technology, which is a magnetic separation technology to recover iron and phosphate from sewage sludge. This technology has been developed in cooperation with Kaumera and Autotech and Delft University, the group of Professor Mark van Loosdrecht. And involved water authorities are Waterschap Brabantse Delta and Waterschapsbedrijf Limburg. They also co-finance this development. And Van Center Zuid, a Danish water utility. Can I have the next slide? I think this development is a really nice example of urban mining. Of course, phosphate rock is now being mined in countries like Morocco and is becoming scarce, and EU does not have its own sources of phosphate rock. So that means that we are dependent on outside countries that might want to keep the reserves for themselves. And as you might know, phosphate is really crucial for our food production. So it will be really cool if we can mine our own phosphate from the sewage system. And in fact, with the technology that we developed, we are actually using mining equipment to mine the phosphate from the sewage sludge. Next slide, please. So we focus on sewage treatment plants that use iron coagulants to remove the phosphate. A lot of phosphate recovery technologies that have been developed in the past are only applicable to sewage treatment plants that use biological phosphorus removal. For instance, Truvite precipitation technology is a widely known phosphate recovery technology, but it only works for the plants that use this enhanced biological peer removal. And these diagrams show the importance of enhanced biological phosphorus removal in several countries. In the Netherlands, we apply it quite a lot, but there are also a lot of other countries, like for instance, UK and Sweden, that really don't use biological phosphorus removal. Instead, they really rely on chemical precipitation with iron or aluminium salts to remove the phosphate. And in the past, there was not really a technology to recover phosphate from these plants. And that's why we started doing some research to see if we can find a technology that can actually do that. Next slide, please. And this slide summarizes the results of our research in the last years, also co-financed by the TKI. And what this slide shows is we sampled sludges from different sewage treatment plants all over Europe. And on the y-axis, you see the amount of iron to phosphorus, the ratio of iron to phosphorus in the digested sludge of these sewage treatment plants. So from left to right, the iron concentration increases. And on the y-axis, you see the amount of phosphate that's bound in vivianiet. So the percentage of the P that is present in this in vivianiet, which is a ferrous phosphate. And you see that if your iron dosage increases, that up to 80 to 90% of all the phosphate that's present in the sludge can be present as vivianite. And this was a really new insight, and it shows that there's a recovery potential if you would be able to recover the vivianite from the sewage from the sewage. The only problem is that this vivianite is present in really small particles, typically 200 to 500 micrometers. Next slide, please. So, this vivianite luckily is found to be paramagnetic, and that was another interesting finding of our research. And paramagnetic means that it becomes magnetic in the presence of a strong magnet. And the small animation to the right shows some of the vivianite that we recovered from the sewage sludge, and you can clearly see the magnetic properties of this vivianite. Vivianite is a ferrous phosphate, which when it's unoxidized is white, but when it oxidizes, it slowly becomes bluish, and therefore it has been used in the past as also as a blue paint, for instance, by Rembrandt and Vermeer. And well, you see the nice bluish crystals that we harvested from the sewage sludge that really shows this nice blue color. But vivianite can also be sometimes a pain, and that's the picture in the middle where you see a pipe that's completely made out of vivianite. And this picture that we got from Waterschapsbedrijf Limburg, where they often have some problem with vivianite scaling problems. But with our technology, we think we can prevent the scaling while recovering vivianite at the same time. Next slide. So how does our concept work? So the concept is based on the idea that, well, iron dosing is always taking place already in sewage treatment plants to remove the phosphate from the sewage. We increase the iron dosage a bit more to stimulate vivianite formation. This vivianite is then formed in the sludge digester, and in the digested sludge, after the sludge digester, we can then use wet magnetic mining equipment to recover the vivianite from the sewage sludge. This then leads to reduced sludge volume that needs to be disposed of. The sludge also has less phosphate and a higher calorific value, so heating value, and that can be of interest, for instance, if you want to go incinerate your sewage sludge in a cement kiln. And the higher calorific value is then of interest for the cement kiln, and also the low P level, because normally P hinders the binding of the cement. So the cement kiln doesn't really like the phosphate. And as a byproduct, you then get a vivianite concentrate, which you could potentially use as iron fertilizer, or can split again into an iron coagulant and a phosphate fertilizer. And I'll come back to that later. Next slide, please. So this is a scheme of the magnetic separator that we use. These are magnetic separators that have been developed for the mining industry. They consist of a rotating ring. This rotating ring dips into the sludge. At the place where it dips into the sludge, there's a strong electromagnet with a magnetic field of 1 Tesla around the sludge. The vivianite then becomes magnetized and sticks to the ring. The ring turns out of the sludge, and then out of the magnetic field, and then you can easily flush off the vivianite from the ring. Next slide. So this ring consists of a matrix with a lot of steel rods, and around these rods you get this high magnetic field that makes that the vivianite sticks to these cassettes in the magnetic ring. Next slide. So we've been working on the upscaling of this technology. We started in 2016, 2017 with a very small lab scale equipment. In 2018, we did the first bench scale testing in Frankfurt at the facilities of Autotech to show the proof of principle. And in 2018, 2019, we operated a pilot plant using a commercial grade magnetic separator of Autotech at the sewage treatment plant of Nereda of Waterschap Bramers and Delta. Next slide. And in this pilot plant, we showed that we could achieve a recovery efficiency of more than 80%. So more than 80% of the vivianite that was present in the sludge we could recover. So the orange dot is the result of the pilot experiment. The blue dots are the results of the bench scale tests, by the way. And you can see that actually the recovery efficiency increased from bench scale to pilot scale. And the y-axis shows the vivianite grade, so the purity of the vivianite concentrate that we recover. And you see that the grade is about 70%. So that means that there's also 30% of other material in our concentrate. That's mainly entrained organic matter from the sewage sludge. And we've shown that if we wash the vivianite, that we can increase the purity up to 95%. So very nice pilot results, and it showed the proof of concept. Next slide. And we are now also working on finding applications for the vivianite that we recover. So one route is to split the iron and phosphate. We are working together also with a Dutch company called Susfos that has developed a similar technology for struvite. And this technology seems to also work for vivianite. And we also have an own alkaline splitting technology. And what you then get is an iron salt that you can reuse again in the sewage treatment plant for the binding of the phosphate, and you get a water-soluble phosphate fertilizer. This splitting technology will require still some work to develop. So we also, for the first applications, we also are also looking for direct use of the vivianite. And one important application there would be to use it as an iron fertilizer, especially olive trees, citrus trees, and vineyards have often suffer from iron chlorosis, so an iron deficiency when they are grown on calcareous soils. And vivianite is already being used as an iron fertilizer for these crops. Another application could be blue paint, possibly, so that has been used in the past. And you also see some tiles to the right, that is tiles that have been made blue, dark blue, blackish with our vivianite. So that also is sort of a painting product. And a real product that you could make, but that requires still some work, is maybe to use it as a raw material for lithium iron phosphate batteries. Next slide. So we think vivianite provides a new approach to phosphate recovery from sewage sludge. The main advantage is that you reduce your sludge volume by 10 to 15%, and this mainly pays for the magnetic separator. In addition, you can recycle the iron and create a circular use of your iron coagulant, which becomes more and more important also when we want to go to a circular economy. And we can recover more than 50% of the phosphorus that is in the effluent of your sewage treatment plant. And well, we also think that the vivianite technology fits in the trend to lower structural effluent limits for phosphate, and that already leads to higher dosages of iron in a lot of sewage treatment plants nowadays. And the lower P concentration in the sludge and the higher heating value of the sludge is also a benefit when you go to, for instance, a cement kiln or a biomass incineration plant to recover energy from your sewage sludge. So that's my presentation about vivianite, and I don't know if you have questions immediately or later, but I'm open to questions.
Well, we can have questions now. If people have any questions, please put them in the chat. Maybe one first question for me, Leon. You said already you developed from smaller scale to pilot scale, and the amount increased that you could recover from the sludge. To go to the next level, what is your need, so to say, to move to the next level or to move to the market?
Yeah, what we want to do now is to build a second version of the pilot that will be in a more automated version of the pilot that we made earlier. And with this pilot, we want to show the long-term operability of the magnet and show and also produce more vivianite. And by producing more vivianite, we can then also work on the offtake of the vivianite, so get applications for that. Because the technology will only fly if you can get a good outlet for the vivianite. But there you always have a chicken and egg problem, that you first need to make more material to be able to develop that application route. And that will be the purpose of this second pilot.
Right. Do you have any forecast about the increase from your current stage to the next stage?
Well, the next pilot will have the same capacity as we already tested, because that is already a commercial grade magnetic separator that we use. And the upscaling of the magnetic separator is not complicated. These magnetic separators are available up to scales of 1,000 cubic meters per hour. And you will never find that much of sewage sludge on the sewage treatment plant. And when you scale up the magnet, it's only a question of increasing the diameter, and there are not a lot.
I don't know why we lost the screen. It's back. Well, there's no questions right now. Then I propose that we go to the next speaker. Our next speaker is Julian Munoz Sierra. He has more than 10 years experience focusing on the development of innovative bioprocess solutions for water, energy, and resources factories in both industry and municipal water streams. Within KWR, Julian focuses on the research to breakthrough concepts and technologies for the recovery of water, energy, and the nutrients and metals in this water. Apart from working for KWR, he's also a chemical engineer at the National University of Columbia, and he's worked for the Technical University of Delft. So yeah, Julian, please, the floor is yours.
Thank you, Matthijs, for your introduction. Can we go to my presentation? Yes. All right. So yeah, so I'm working currently at KWR in the team water treatment and resource recovery, and today I'm going to be talking about the TKI project, recovery of metals from water, sludge, and fly ash. Next slide, please. So yeah, for those people in the audience who don't know, brilliant science practice in KWR is KWR motto. So our strength lies in the translation of scientific knowledge into practical solutions in the Dutch and international water sector. We develop strategy, initiate, support, and execute projects, and stimulate our colleagues to expand the activities of KWR also internationally. In our WaterWise research program, we work on the optimal management of the water cycle, having circular economy as key driver, and of course the UN Sustainable Development Goals in mind. So the research at KWR is embodied in these 5 research programs you see in the right side of the slide. One of them is sustainable water cycle, in which resource recovery is one of the main topics. Next slides, please. So what was the motivation behind this project? So mainly there was a report on the exploration of possibilities of raw materials in wastewater treatment plants by STOA, in which the metals belong to the unselected raw materials, because basically still a lot is unknown. And in that report, it was pointed out that the concentration in wastewater or sludge for all metals was not yet known, and especially of the rare metals where a potential global shortage is expected. Next, please. Next. So we carry out a preliminary study in which was clear there was still hardly any insight into the concentration on the form or speciation of those various rare metals in the different flows of the wastewater, sludge, and fly ash change. And it was clear that there are opportunities for the recovery of metals such as copper, zinc, gold, and palladium. And of course, that the removal of metals also improve the quality of any byproducts from these chains, and therefore there could be a market opportunity. Next slide, please. So we set research targets towards opportunities for recovery of heavy metals and rare earth metals in the water cycle. And we wanted to explore suitable technologies to remove and recover them, and to carry out some proof of principle tests to determine the extent of removal and recovery that could be achieved. Next, please. So here we can see all the companies, water companies and water authorities involved on this TKI project. So that it was basically a very good consortium, very proactive, and like we reach very good results. So in the coming slides, I will be just giving you sort of insight of what we achieved and what we will learn. So next, please. So we focus initially on the detection of metals from influent sludge and fly ash, and there were samples taken from different streams. Basically, these streams were a drinking water production facility, from where 3 streams were taken into account, 7 streams of 4 wastewater treatment plants, the fly ash of the incineration of wastewater treatment plant sludge, and the compost of, again, also municipal sludge. So we measure the metals from all these streams and on all the cycle by inductively coupled plasma mass spectrometry, so ICP-MS method that we actually develop on site. So we choose to use ICP-MS because you can scan a whole range of elements, including metals, with only 1 sample. And we wanted to also go to lower detection limits. So we actually, right now at KWR, we can measure 64 elements with the ICP-MS to concentrations lower than or up to 0.01 microgram per liter. That was actually a good achievement from this TKI project. And that allow us also to continue the research towards looking at the whole chain and how the metals are basically distributed. So next slide, please. Also, by looking at the standard decree implemented for the fertilizers art, it was clear that zinc and copper are critical to enable at some point the use of sludge for agriculture. And that also tells us that therefore the removal of metals can lead to an improvement in both in the effluent quality and in the sludge quality, and thus potential new sales opportunities, or basically the use of sludge in the agricultural sector. Next slide, please. So from this project, we also presented an overview from the 64 metals present in each stream. For example, this figuring one of metals in fly ash, in which the kilograms of metals per year was quantified, and also led to an important insight on the load of metals, and we could from there make a cost analysis and scenarios of recovery, also make a short list of which are the most important metals that we could focus on for further application of technologies to recover them. So next slide, please. It was also important to determine, for instance, where were the metals present in the effluent. So for instance, in the Amerford wastewater treatment plant, you can see from this figure that most of the metal in the effluent, which are in the x-axis, were in the soluble state, but some metals, especially aluminium and lead, but also copper and zinc, were like more than 50% connected to particles present in the effluent, which also tell us that already in the primary step of sedimentation, primary treatment, metals, I mean, those metals will be going directly to the sludge chain. Next slide, please. Right, so we got you know, the 64 elements with all the concentration also in the sludge chain, let's say. So both in the compost, in the compost and in the fly ash, in this case from GMB and HPC. So almost all the elements were above the detection limit that we set in our method. Usually about 3 times higher concentration were found in the ash, in the fly ash, compared to the compost. And based on geological scarcity, the presence compared of the current and expected future consumption or the supply risk for near future allow us to look at the available concentrations and loads, and from there examine or come up with a short list of metals that could have a potential or more interest to be recovered, in this case from the fly ash or compost side. And this short list includes metals like antimony, indium, silver, copper, tantalum, palladium, zinc, cobalt, gallium, tungsten, iridium, cerium, and titanium. Of course, for the different companies involved, there were different metals of interest, but looking at the priorities, we also come up with a short list of 10 metals. Next slide, please. So what did we learn? So we got a good insight in the presence of metals in the water cycle. We already know that the highest concentration were found in the fly ash, and therefore, yeah, it was a good insight or a good result to look further into the fly ash. And at the wastewater treatment plants, we already know the distribution of metals over particles, influent, effluent, and the sludge. And we also conclude that the difference between the sludge samples between the different wastewater treatment plants was basically limited. So they were very, very similar. Next, please. That also, next. Yeah, that also allow us to basically conclude that improving sludge quality, that for improving the sludge quality, we should focus on the upstream, the influent, for instance, for copper and zinc, in order to comply with the limits, or downstreams for getting higher yields on recovery, in this case, fly ash. So, and then of course the fly ash with the higher concentrations gave us the higher possibilities for recovery due to the higher load, because at the end it's a central sludge treatment from multiple treatment plants. Next, please. Yeah, so we look at different technologies and processes at the end, right? So in which basically we had we tested chemical precipitation, ion exchange, electrocoagulation, and electrolysis, and of course acid leaching for the fly ash, to basically make a proof of principles. How much could we remove and how much could we recover? And then we also compared already system processes in the market, like AlphaSOR, EcoFos, S2Fos, like how can actually this process could be coupled to the removal or the recovery of metals. Next slide, please. Yeah, next. Right, so just to give you a quick overview. So we look at what precipitation to determine what is possible to create a precipitate from fly ash digested, and how much of metals could we actually gain from there at different steps. So we move actually from fly ash solution, moving from pH 1 to pH 3 and pH 5, in which basically we could determine the concentrations at different pH, as can be shown here in the figure on the right side, and in which we also basically conclude the different content of what were the major elements, the metals present in the precipitate. For instance, looking at these 10 elements that are in the x-axis, we could say that iron was the major metal contained in the fly ash, and the majority of copper and zinc, so about 86% and 89% precipitated already at pH 5. We also could basically already say that a combined process with other technologies could optimize the recovery and the purity of metals, and minimize, of course, the use of chemicals that could increase operational costs. In this case, the use of a base in order to increase the pH. Next, please.
We are sorry to interrupt, but considering the time,
I'm in the last. Yeah, I'm in the last. Yeah. So. Okay. So we also look at the combination of ion exchange application with precipitation, in which basically we look at different possibilities using different type of resins to target specifically the removal of copper and zinc. We also look, next please, at the electrocoagulation. Next. So we also look at electrocoagulation, and again, we also came to conclusions about the percentage of removal. So my take-home message basically is that metal recovery opportunities from the sewage influence sludge fly ash chain with the target of achieving a more circular water cycle in the future. So there are plenty of recovery opportunities, and we are actually currently working on a new research idea proposal for a TKI project, and I will be very happy to receive comments or people who are interested to join us and to follow up with that. With this, I just finished my presentation. Thank you very much for your time and for listening.
Thank you, Julian. There are some questions from the public. Maybe one one that we can answer now is from Jan Perenboom. He said that you're talking about fly ash. How about bottom ash?
Yeah, that's a good question. We look only at fly ash so far, and that was basically because of the centralized, basically how the sludge treatment was centralized, and because it was one of the main interests from HBC. We didn't look at the bottom ash, but we know from what Germany and Switzerland are doing that could be also a quite interesting source of metals to look at. Definitely, yeah.
All right. Thank you. There are some more questions, but we'll come back to them in the discussion. Then now, if we can move to the next slide, I would like to give the floor to Sjoerd Kerstens. Sjoerd is graduated in environmental sciences in 2002 and got his PhD in 2016 with research to the potential stimulus for sanitation in developing countries by the resource recovery. After his graduation in 2002, he worked for the spin-off LEAF from Wageningen University and GHV, sorry. The last 10 years, he's been working for Royal Haskoning, DHV, and for them, he worked or he started working in Jakarta in Indonesia as a sanitation and water expert. And since 6 years, he is account manager and process engineer with the business units Nereda, and he will tell us more about Nereda and Kaumera. So, Sjoerd, the floor is yours.
Thank you for your introduction, and happy to be here. I was asked to explain some more about Kaumera, which we think is really a stepping stone towards a circular economy. But I cannot explain Kaumera without first introducing the Nereda technology. So if you go to the next slide. The Nereda is an aerobic granular sludge technology for the treatment of wastewater, both domestic and industrial. Was already developed back in the 90s, where the development started with Mark van Loosdrecht in his laboratory at Technical University of Delft, and where Royal Haskoning DHV got involved in the early 2000s. And together with the Dutch water authorities, we actually had this trinity, so Technical University of Delft, Dutch water authorities, and Royal Haskoning DHV to further develop this Nereda technology. Of course, the main driver were the more stringent effluent requirements in terms of nitrogen and phosphorus, but already we had quite some technologies that could reach low effluent quality standards. But there were some, because of the changing earth and urbanization, there were some other drivers actually that led to the development of the aerobic granular sludge technology. And if you look at it both from CAPEX or OPEX, you see on the left hand side, you see the more CAPEX related issues. One is footprint. We see more urbanization. The price of land increases drastically. And therefore, actually, we want to reduce the footprint of wastewater treatment technologies. And at the same time, we want to reduce the amount of mechanical equipment that is needed inside these technologies. Secondly, more from the OPEX point of view, we, you all know the fossil fuels crisis that we have, and we want to reduce the energy, of course, the energy that is required to treat wastewater, but also reduce less chemicals, and especially iron chemical, which is now used for phosphorus removal. So we wanted to move more towards the biological pee removal. Obviously, we want to facilitate the operation by having less operator oversight and have less maintenance of the mechanical equipment. So next slide, please. So the combination of these drivers actually led to the development of the Nereda technology. And the Nereda technology is operated as a batch system with 3 phases. You see on the right-hand side, you see these 3 phases. So wastewater is introduced from the bottom of the reactor while simultaneously pushing out the water that was treated in the previous batch. The second phase is the aeration phase, and the third phase is the fast settling phase. And maybe this seems like a conventional SBR type of cycle, but there are some notable differences. And the main difference is actually the type of sludge that is produced. Where in a conventional SBR, flocculant sludge is used, or conventional activated sludge system. We produce aerobic granular sludge. And the advantages is the very fast settling of this sludge. Consequently, we can also operate at double the amount of sludge concentration in those reactors. So to treat the same amount of wastewater, we need half of the volume. If you would cut open such a granule, and that's the picture you see at the left lower corner, you actually see that it's not just one type of bacteria that is doing all the conversions. You see different layers like a biofilm that are responsible for the conversion. So on the outside of this granules, the part that is exposed to the oxygen, you see the nitrifying bacteria and the conversion of COD and BOD, whereas more towards the inside, you see the anoxic bacteria for denitrification. And also you have the PAOs, the phosphate accumulating organisms, which are basically spread everywhere. And by having aerobic conditions, we have this BioP removal. So in one of those granules, we are able to remove COD, nitrogen, and phosphorus. Obviously, we don't need clarifiers like you have in the conventional activated sludge or moving decanters or mixers. And all of this together actually results in the advantages, which were the original drivers that I mentioned before. Okay, next slide, please. So, as I mentioned, we already started this development back in the 90s. At the time, it was Technical University of Delft. And over the years, we have been gradually, but especially the last 5-6 years, exponentially almost increasing the number of full-scale reactors. One more, please. Next slide. Yeah. So at this moment, we are having over 80 projects worldwide, and the biggest one actually is the Rings End pilot plant in Dublin, treating the wastewater of 2.4 million people. We recently won the Jeddah project in Saudi, which is also a major milestone. But also we have many plants in the Netherlands. We have 2 projects in Germany, Switzerland, Scandinavia is plus well, Asia, the North America, South America. Actually, we're on all continents at this moment, and we applied for industrial wastewater and domestic wastewater on all different climate ranges. So the next one, please. And this is actually the bridge. So that was the introduction of the Nereda. Why I use the bridge is that, can you click a few more there, please? Yeah, because what was found, and it was actually already found in 2008, and again, a lot of credits there to the Technical University of Delft. It was found that in this granulation process, which is done by the phosphate accumulating organisms, at least they play a very important role there, also a sort of biopolymer was produced. And can we have one more? And this biopolymer is like a glue, actually, which holds the granule together. But it also represents a certain component, which was later labeled as Kaumera. And if you click one more, please. Yeah, and this Kaumera, so which can be extracted, contains mostly proteins. So 3 minutes, I just started. Okay, I have to quit. Hurry up a bit. So how do we do this extraction? Once you got the waste sludge of the Nereda, which is extracted every time, we first have a thickening step, and then we can extract the Kaumera by first heating it and bringing it into alkaline conditions. In that way, we dissolve the polymer to the water phase. By having a centrifuge, which is step 4 here, we separate the remaining solids from this polymer, which is dissolved. And then by number 5, adding an acid again, we precipitate this polymer again. And we can, in this final centrifuge stage, we can separate the water and this final Kaumera product, which is a number 6. Next one, please. Why it's interesting, of course, is the application possibilities. This combination of proteins and polysaccharides has several promises. It can be used as a coating agent. For example, if you have fertilizers and you want to control the release of those fertilizers, you can coat it. But it can also be used as an adsorber. It can have like 20 times its own weight in water adsorbent. So for a future application, you could consider using it in diapers. At the same time, it is water repelling, depending on the processing that is used afterwards, properties. So you could use it for coating of paper. Currently, we are already using it as a biostimulant for root protection and better water preservation, and it can be used as a binding agent. When combining it with clay, you could have like a bio nanocomposite properties, and that's future music, by the way. It can have very strong properties, for example, in fire retarding, which is shown in the number 6. If you go to the next slide, so you can click 3, I think, yeah. Why is this relevant? Of course, while taking out part of the polymers, we reduce the amount of sludge that needs further processing, which is of course a cost saver, but it's not the main driver. Much more important and interesting, I think, is the fact that we are producing something. Previous speakers spoke about recovery, phosphorus or iron from waste sludge. In this process, we are producing a new product called Kaumera. And if you look at it, we actually have a new purpose of the sludge, and it actually becomes, that's at least what we would like to see, also a driver for the development of Nereda. By having a purpose from your Kaumera, you first require Nereda, and in that way we got a sort of flying wheel, which with a synergy value. So we're producing something valuable from wastewater. If you go to the next slide, which is almost my last slide, and it's also a nice bridge to the next one. Kaumera was not developed by us alone, by far not. Again, we had the Technical University of Delft and STOA there. Two other important parties are the Waterschap Rijn en IJssel, and the next speaker is Maarten from that water authority, but also Vallei and Veluwe. And also very important Chaincraft, who is looking very much at the the application purposes and increasing that range for the use of it. Where we are at the moment, and just bridge back to Leon Koving, he mentioned in order to have this chicken and egg story, you need first to produce amounts that can be used for testing of applications. We are currently in that very process. So, 2 years ago, 1.5 years ago, the first one, Kaumera extraction installation was opened in Zutphen with the potential to treat 2,800 tons of dry solids of sludge per year. And we are very much in the commissioning a startup of a second one at Epe, which was also the first Dutch site for Nereda, to treat municipal wastewater for about 250 tons of dry solids per year. I think that was my last slide. Can you go to the next one, please? Not the fully last slide. Yeah, maybe just to, this is always a bit of bragging, but it's not ourselves bragging. We've been recognized for both the development of the Nereda, but also the Kaumera in several recent announcements. Recently, we got a Water Technology Company of the Year, but also the Nereda was mentioned as the groundbreaking technology of the decade. And last year, we won the Aquatech Innovation Award for the Kaumera. So yeah, we're very proud of this, and we see a potential range of application methods, and I'm happy to take any questions if you have some. So thank you for your time.
Thank you, Sjoerd. I'm sure we come back to this in the discussion. I think Kaumera is one of the, or Nereda is one of the, how do you say that, the most apparent success stories of the last years, perhaps in terms of marketing. So it's very interesting. Thank you for the presentation. As said, we'll come back to it in the discussion. Now we move to the next topic, so to say, in our webinar about opportunities in the Netherlands and the Balkan. We'll start with Maarten Schaasma. He graduated in 2009 in environmental sciences at Radboud University, and since then he's been working as strategic advisor at several organizations. In the last 4 years, he's been working as senior policy advisor and process manager at the Water Board Rijn en IJssel. Next to that, he is the chair of the working group on Kaumera in the Energie- en Grondstoffenfabriek. Sjoerd, of Maarten, sorry. Maarten, the floor is yours.
Thank you very much, Matthijs. Yeah, I will give a short overview of the actual situation in the Netherlands regarding raw material recovery from sludge. I'm giving this presentation on behalf of the Energy and Raw Material Factory, which is a concept and network organization of the 21 Dutch water authorities. Please can I have the next slide? If you have a look at wastewater, already in 2009, the concept of the energy factory was launched. Wastewater contains about 8 times the amount of energy we need to treat the water. Later on in 2012, we also included the recovery of raw materials within the concept, and since then it's called the Energy and Raw Materials Factory in Dutch, Energie- en Grondstoffabriek. Can I have the next slide? 3 years ago, we decided to focus on a sort of top 5 resources from water, also including the water system. The top 5 was then biomass, bioplastics, phosphorus, Kaumera, and cellulose. And maybe in that case, we forgot our most valuable resources in times of water shortage, which is the water, of course. So that's also included in the concept of water factory. And also we have the energy we can still recover. So this sheet is containing the focus we have now as the energy and raw materials factory in the Dutch water sector. Can I have the next slide? Where are we now in the Netherlands? We have phosphorus, we have research on recovery of bioplastic as PHA, the production of cellulose, Kaumera, and we also included the other products more or less from the energy factory, not the biogas, but the carbon dioxide, which can be recovered and sold to greenhouses, and the production of green gas from the biogas. Phosphorus is now mainly recovered as sulfide. We're doing researches on the production of vivianiet, as Leon Korving presented, and we are working on the recovery of recovery of phosphorus from the fly ash, but it's still not in production. Besides, at this moment, we are working on a pilot scale production facility in Dordrecht on the recovery of PHA, but it's not there yet, so it will be presented on the next slide in a few minutes. We produce cellulose on different locations in the Netherlands, which is at this moment unprocessed cellulose. We're doing different researches on it, and it's being applied at this moment in asphalt, so for road production as more or less as a binding agent. We have 2 facilities for production of Kaumera, one in Zutphen with an actual production of about 315 tons organic dry solids a year, and one in Epe with 50 tons organic dry solids a year. And then we have the carbon dioxide and green gas production, and for green gas, the actual production is about 10 million cubic cubes a year. Next to the top 5 of resources, we of course have other resources we are doing research on, like the recovery of nitrogen, which is already recovered by GMB in Zutphen as ammonium sulfate, and it can be recovered from the centrate after sludge digestion, or just in the water line by concentrating the effluent, which is now some research is done, for example, in the cold water research together with other water authorities and KWR and Royalsk and DHV. We already had the presentation on metal recovery, and other research lines are the production of fatty acids from the primary sludge. Can I have the next slide? But what's then the potential in the Netherlands? Added to the table on the previous slide, we added our expectation for the next 5 years and the potential in the Netherlands if we treat all sludge, focusing on the specific raw material. For example, for phosphorus from the fly ash, we can recover about 8,000 tons a year. As a sulfide, about 1,200 tons a year, or in total, the potential is 12,000 tons. For bioplastics, if you take the whole country, so all the sludge from the Netherlands, the potential is about 25,000 tons of PHA. For cellulose, it's 180,000. And for Kaumera, if we would say for the whole Netherlands, we produce granular sludge, like presented by Stuart Keston, you can produce about 60,000 tons of Kaumera a year. Yeah, and also for green gas, if you take the actual production of biogas and you would make green gas from that amount of biogas, you would get around 70 million cubes a year. For some resources, I included a star behind it because there is some conflict. So, for example, recovery and production of Kaumera is competing with bioplastics, or is competing with biogas production. So all the amount of resources you recover and sell as Kaumera containing containing carbon as a protein content, it cannot be used again for production of biogas. So there is some competition between the resources. This was my short introduction in 5 minutes on the potential in the Netherlands.
Thank you, Martin. Then I would now like to move to our last speaker of today, Darja Krajic-Kok, working at NWP. Darja graduated first from Belgrade University in biochemical engineering, and after that she moved to Wageningen University, where she studied environmental sciences. She completed 2 master theses. The first one dealt with the evaluation of wastewater treatment technologies in the southern provinces of Vietnam, and the second thesis dealt with the removal of birth hormone control in pills from domestic wastewater. She worked for 13 years with the company Leaf, the spin-off of Wageningen that I mentioned earlier, where she was responsible for projects aiming at water, nutrients, and energy recovery from sanitation systems. Since 1 year, she's working at NWP, where she's responsible for developing countries, or developing opportunities for the Dutch water sector, especially in the Balkan region. Darja?
Thank you, Matthijs. And thank you for inviting me. It is a pleasure to be here and represent the Netherlands Water Partnership together with, of course, joining the event with the Water Alliance and Envaqua. Netherlands Water Partnership is the largest water network in the Netherlands, and we have a motto: if you want to go fast, go alone, and if you want to go far, go together. That's actually an African proverb. And today I will just give you a glimpse of the situation in the Balkan countries related to the topic today, having also 5 minutes that I will try to keep in mind. So next slide, please. Within Partners for Water program, there is a focus on Balkan countries. And Partners for Water is financed by RWO, made possible, and also by the Dutch embassies in the region. Having in mind what happened this year, we switched to completely to online events, and we organized this year 2 very different water events, dealt with water management for climate resilient Balkan cities, and also recently about wastewater and sludge management for circular economy in the Western Balkan. Next webinar will come in December, and I will tell you something and invite you also, completely again different topic, but good to share the word within your organizations. So next slide, please. And where are we now? We talk about Balkans, and for Partners for Water country, we address Slovenia and Croatia, which are already EU members, but also Bosnia and Herzegovina, Serbia, Montenegro, Kosovo, North Macedonia, and Albania, that are all candidate countries, whereas this is a bit dated map, because also North Macedonia and Albania should be darker red. They are entered the negotiations for EU. Having said that, environmental chapter is a big thing in the EU negotiations, and all candidate countries are making huge investments in meeting the environmental chapter. And this is now I want to show you one graphics that was also brought to my attention. Next, please. Also by actually Sjoerd's colleague from Royal Haskoning DHV. This is actually where we are going as a humankind. And we can also see the trend based on where we are now with reaching to EU legislation, but also the trends in the Netherlands. You can make your own, deduct your own conclusions where we are now, where we would like to be with the Homo circularis, of course. So then the next slide, please. Like I mentioned, EU and joining EU is the big driving force for the countries in the region. And you can see, for example, where the light green is a secondary treatment and the dark green is the tertiary treatment, how the countries are doing. Croatia on this list is the only country that is member of EU. And you can see that actually they're still not meeting the European Urban Wastewater Directive, but they made a huge progress. Again, this is a dated graph, but the most recent publicly available. And you can also see the trends in other countries, such as Serbia, where they're mainly secondary treatment as well, but mostly there is no wastewater treatment yet. So Serbia took also billions of loans to invest in wastewater management. Next slide, please. But coming back to sludge management, this was also one of the reasons that I was invited. It is a big issue also in the region. The countries that have joined the EU and that have already wastewater treatment plants installed, they have an issue with the sludge management. So for example, Croatia and Slovenia, they were exporting since last year their sludge for further treatment in Hungary, where apparently it was a big it was a big issue there because it was not properly being treated. So Hungary closed its border for Slovenian and Croatian sludge. So is it only there an issue? It's a question, or is it more international issue? Next slide, please. So this is also one of the headlines from H2O magazine, where it was highlighted what was happening last year in the Netherlands, where actually when incinerator capacities went down for more than a half. There was a big issue, and it remains a big issue in Europe because we are dealing with it as end-of-pipe solutions at the moment. But I'm really happy to hear about innovation, but also to think about how we can design actually out of the solution. Next slide, please. We as NWP earlier this year, when the COVID crisis started, we reached out to Wageningen University, and together with the students, we gave as a topic to investigate sustainable sludge treatment options in the Netherlands. And soon the summary of this publication will be available of the student research. Next slide, please. This is just a glimpse of the selected EU countries. You can see actually the upper part is like Sweden, with 100% being connected to urban wastewater treatment and treated. And you can see, for example, lower where the Serbia is, and you can see also where Romania is, which is also EU member state, but you can also see where Slovenia is. And Slovenia is actually doing a lot of efforts to close the cycles, and the public is objecting to incinerators, and they're searching for resource recovery, and they're searching for circular solutions. And they are also improving their actually the wastewater treatment and sludge treatment in their capital, in Ljubljana. So that's the right-hand side. That was also what took place last year. And we would like to also be part as a Dutch water sector on their journey in their search for circular solutions. And especially, maybe next slide, please. I would like to mention that next year in 2021, NWP will be organizing Green City Dialogues, because we are building up on EBRD's Green City Action Plans, but also to organize the sector visit to water event in Slovenia in the second half of 2021, when Slovenia will be chairing the presidency of the EU Council. Also, I would like to invite you to the Business Week of Central and Eastern Europe, where we'll be also organizing a webinar on December 9, completely different topic, but again, we'll try to bring circular solutions for river cleanup. And also in the virtual roundtable talks, NWP will address the green agenda for Western Balkans. So that was actually 6.5 minutes, but I did my best. So this is in short what we do, and this is the team that is dealing with it, and Yara is also here also supporting us today. So thank you.
Thank you, Daria. And then thanks to all the speakers first. Please, Yara, can you stop the recording as we move now to the discussion?